Okay, in this video I'm going to show you some of the details of making the plot of your experimental data on loss in the hallway at Donovan Hall to see what the loss exponent is. And it may differ from 2, it turns out. Well, what we've seen is that the Friis equation for free space loss is something like this. P of r is equal to lambda squared all over 4 pi quantity squared r squared. Okay? And what I'm going to do for the purposes of this exercise is write this as C1 times r to the minus C2 power, where C1 and C2 are constants. C1 is lambda squared over 4 pi squared, and C2 is 2. This is equal to our exponent. And I'm going to go ahead and leave that as a variable from now on, because, as I say, we're expecting perhaps that the indoor environment behaves differently. It's called the loss exponent. The indoor environment behaves differently from free space. This is for free space. And it follows the inverse square law. Okay? So we might expect that our loss exponent is less than 2, meaning that the power doesn't die out as quickly in a situation where we have a waveguide effect of a hallway. That is where the walls of the hallway are sort of reflecting the RF waves sort of down the hallway and actually enhancing, decreasing the amount of loss. So instead of, if we have a source here, instead of the RF energy going off in all directions, if we are in a hallway, some of the energy that would have gone off in other directions is now bounced back towards our receiver here. Okay? So here's our transmitter. And so that, I hope, makes a little bit of sense. And we may have a situation where we have C2 greater than 2 if we have large losses indoors due to things like walls, multiple reflections off of cubicles or things like that. Okay, so we might expect that we have an exponent less than 2 in our experiment down the hallway. Okay, so that's the introduction to the loss exponent. Oftentimes that's called alpha. And first thing to note about this equation is that if you're going to deal with it experimentally, you've got a problem at r equals 0. You can't measure the RF power at r equals 0. This equation says that it diverges with the r in the denominator like that. And so what we're going to do, so as r approaches 0, then the P of r diverges. And so that's a problem. So we're going to choose a non-zero reference distance. And we're going to call that R naught. So we're going to let P of R naught be C1 R naught to the minus C2. Then I can solve for C1, which is P of R naught all over R naught to the minus C2 power. And finally I can write that I can rewrite the equation in terms of this as follows. So P of R now is C1 r to the minus C2, but C1 now is P of r naught all over r naught to the minus C2. And this whole thing can be then rewritten as P of r naught r over r naught. So we're going to measure our distances relative to that reference distance r naught. Okay? And we can convert this equation into decimal units by taking 10 log 10 of both sides. And when I take 10 log 10 of the left-hand side, it's simply P of r in decimal units. And this is 10 log 10 of a product, so it is the sum of those logs of, now I have r over r naught to the minus C2. And this first term on the left is just P of r naught in decimal units. And now I have the log of something raised to a power. And so that becomes, the power comes out front. So I can write this as minus 10 times C2 log base 10 of r over r naught. Okay? So this is basically what we're working with here. So we have P in dB at distance r is this, and this is the equation that we're going to work with. And now what I'm going to do is I'm going to ask the question, what is the loss relative to the reference point r naught? Okay, so I'm going to say that L is equal to loss relative to the power at r naught. And I'm going to say that that is then equal to P naught minus P of r. And these are both in dB units. Okay? And so this is going to be greater than 0 because P at the distance r naught, that has greater power. Let me try to fix up my notation here. Okay, so this is going to be a loss value greater than 0. And in fact, this is the value that we put into our spreadsheet. So I'm going to write that out here on the next page. L is P naught in dB units minus P in dB units at distance r. And looking at the equation, we can see that this I forgot to define that P naught in dB units is equal to P dB units at distance r naught. Okay, that's what I mean by P naught. And so if I take that, then I get 10 C2 log r over r naught. Okay? And that's the equation we're trying to plot in our spreadsheet. And in fact, we're going to go ahead and let r naught be 1. It's arbitrary. It's in arbitrary units. So whatever units we use, whether they're units of floor tiles or feet or meters or anything, we can go ahead and set r naught equal to 1, and then we're going to have L equal to 10 C2 log r. Okay? And that's what we're going to plot. We're going to go ahead and plot L versus r with a log scale on the r. Let me show you a little bit of detail of how that works here. We're going to go ahead and plot r horizontally and L in decimal units vertically, we're going to use a log scale on R, meaning that R is going to jump by a log 10 scale. It's going to jump by factors of 10. Okay, and on the vertical axis, we're going to start at a loss of 0. Because at R equals 1, we have a loss of 0. When I plug in 1 for R here, the loss value is 0 because the log of 1 is 0. And then the loss is going to go up maybe 20, 40, 60 dB. And what we're going to see then when we plot our data, hopefully, is something that's fairly reasonable. Believe me, it's not going to be a straight line, but if you see something like this, what we're seeing here is that we can measure the slope of this because the log of R, base 10 of R, is 0, 1, 2, 3. And so what we're seeing here is that the slope is in fact 20 when we look at it relative to the log scale. Okay, so here's our log scale, and you can see that the rise is 20 where the run is 1. So we have a rise of 20 over a run of 1 on the log scale, the log numbers. And again, from 1 to 2, we go up by 20 dB. From 2 to 3, up by 20 dB. So the slope is 20 there, and this is something that you would expect to see if C2 were equal to 2. Okay? And so what we're going to look for then, when we make our plot, we're going to use Excel to plot our loss data, this value, relative to the loss at R equals 1, and we're going to plot positive values, and we're going to then measure the slope on the log R plot, meaning every time R goes up by a factor of 10 on the axis that we have, we consider that a step of 1 in the log. Okay? And so that's the theory behind what we're doing. And I hope that helps. I'll show another video with some data actually on a spreadsheet.